Performance and execution time analysis of optimal controls in hard real-time environment. È un lavoro svolto insieme ad Andrea Bonci, Sauro Longhi e Giuseppe Antonio Scala, ma presenta Giacomo Nabissi. Prego Giacomo.
Sì, grazie. Okay. Hello everybody, I'm Giacomo Nabissi and I'm a PhD student of the Department of Information Engineering from the Polytechnic University of Marche. Today I'm going to present our work, performance and execution time analysis of optimal controls in a real-time environment. Okay, some motivations. Many engineering fields have to deal with real-time system where temporal constraints must be fulfilled to avoid system failures. Therefore, the behavior of the computing system must be predictable at the design stage. And for this reason, estimation of the code's worst-case execution time has received lots of attention because in this system is a fundamental requirement to guarantee at least a temporal upper bound for the code execution. Nowadays, for a real-time application, the requirements are solved via hardware using this multi-cores embedded board that allow the computation of a deterministic execution time. So the idea of our work was to compare first optimal control technique implementation through a classic performance analysis and also through an execution time analysis, taking advantage of this board. Okay, so what we have done is we experienced another real-time embedded solution for optimal controllers, in particular the linear quadratic regulator, the model predictive control, and the state-dependent Riccardo equation. The first two are the linear version, while the state-dependent Riccardo equation is a nonlinear controller. How we developed a card pendulum prototype with an real-time embedded board integrated. The board hosts the control algorithm. And why we do this? Because we want to study the controller implementation characteristics, especially in terms of algorithm complexity. What about the novelty of this work? First, it is proposed a novel kind of analysis, both for performance and for worst-case execution time of the code. The second one is that through this new analysis, it has been possible to evaluate the limit of the classing implementation for these controllers, and it has been found a way to improve the execution time of the nonlinear controller. Something about the methodology. It has been derived first the model of the card pendulum in discrete-time linear-like form, and this was used for the simulations and to design the controllers. The LQR, MPC, and SDRI techniques are designed to stabilize the pendulum in the upright position. At the same time, the card must maintain a certain distance from an obstacle. Regarding the nonlinear controller, the discrete algebraic Riccardo equation is calculated online using a Newton-type iterative procedure, and this is a classic approach. Also for the LQR and the MPC, we use a classic approach in the first development. Some characteristics of the board. The hardware platform is from the XMOS family, and this hosts 4 deterministic core. And the board provides parallel computing, and in this way it's possible to distribute the task of all the control application. And this architecture gives determinism to the operation, and it's possible to calculate 2 features, in particular the best case scenario and the worst case scenario related for each control task. And in particular, the worst case scenario can provide an upper bound limit to consider the worst case execution time and set the temporal limit of the application. Some result. The first test was to prove the consistency of the model that we derived, and also to prove the consistency of the controller implementation. So we compare the simulation with the experimental results, and how it's possible to see the trends are really similar. In particular, in the first graph, we have the angle of the card pendulum. In the second one, we have the card position X. And the third one, we have the control effort U. And in particular, these results are for the nonlinear controller. And how is it possible to see the trends are really similar, but are not perfectly the same, because achieve a perfect model was out of the scope of this work. So it's just to prove the consistency. Something about the performance evaluation. So first we test the linear controller and the nonlinear one in a best case scenario, so in linear condition, and all the controllers were able to perform the task. As a second test, we triggered the nonlinearities of the system by imposing a pendulum angle out of the linear range, and how it's possible to see in the graph on the left of the screen. Only the nonlinear controller was able to control the system and to accomplish the task. So we were also interested in the execution time. So through the XMOS board, we calculate the best case scenario and the worst case scenario for each of the tasks. And the worst case scenario provide the upper bound limit for the real-time application. And in particular, also this is useful in general for during the design stage to set the closed loop sample time of the application. But however, how is possible to see in the table, the nonlinear controller takes almost 4 times the linear controller. So it's really time consuming. For this reason, we start to investigate how to improve the execution time of the nonlinear controller. And finally, we found 2 ways. Following 2 criteria. The first one was to evaluate the similarity between 2 numerical matrices, considering 2 consecutive instants, k and k plus 1 in discrete time. And the second one was an adaptive P initialization, because it has been experienced that an adaptive P initialization for calculate the discrete algebraic Riccardo equation can really improve the execution time of the nonlinear controller. How is it possible to see in the table the best case scenario and the worst case scenario? In the best case scenario, that means in the linear range, we obtain an execution time close to the linear controller, also for the nonlinear SDRA. In the worst case scenario, we decrease the VChet of the algorithm by 35% almost. At the same time, in the low part of the screen, we can see the angle, the position, and the control effort, and this was to compare the performance of both the nonlinear controller. We can see that the performance are the same. So we obtain same performance, but with less execution time. So in this work, what we have done is to provide a method to evaluate in a deterministic way the execution time required by, in general, the controller, in particular for embedded devices. And once we evaluate the performance and the execution time for 3 of the most used optimal controller, we show a way to improve the execution time of the nonlinear one by proposing a new method that we called MET-SDRAI. But in general, these results can be useful for the field of control system engineering, especially during the design stage in real-time system, where temporal bounds have to be fulfilled, also taking into account all the other functional specification of the application. But however, all the results that I presented are already available in an article called Execution Time of Optimal Controls in Hard Real Time, a minimal execution time solution for nonlinear state-dependent Riccardo equation, which has just been published on IEEE Access Journal. Thank you for your kind attention.
Thanks a lot, Giacomo. So, yeah, thanks for a clear presentation. And actually, we have 10 minutes for questions. So I would encourage the audience to make questions through the chat. In the meantime, maybe I have a question. So how you envision extension of this work? In which direction? What is missing?
Okay, in which direction? Probably we want to understand the link between the execution time and the performance of the controller in general. So what happens if you can decrease the execution time? You can reach also some new stabilization performance or asymptotic stabilization performance, stuff like that. We want to also to evaluate more complete system or the high order system to understand if it's possible also in that kind of system to decrease the execution time. Yeah, this yeah.
Okay. Are there any questions? Can't actually. There should be through the Zoom webinar chat, correct?
Yes.
I cannot see any. Yeah, apparently. So you experimented your work on some on this car and pendulum, but is this for some lab?
Yeah, we test in our laboratory. Me and my colleague Giuseppe Scala, he worked on the implementation, and we are working together on this topic, and also with our professors.
So, yeah, but this is going away also to get involved students to try, since there is much work nowadays on educational involvement, like remote lecturing, where you make try different approaches on a device and check. So you haven't thought about possibly opening to students or if you find an efficient embedded.
Yeah, the students are already testing some board for different application, more easy, maybe linear application or just simplify, but they are already coding in low level. So like in our work.
Yeah, like in your work. Okay, let's leave time for further questions if there are any. Okay, I have a question.
Hi. I'm Mauro Franceschelli. So I was actually, I just have a curiosity. So here the focus is on deterministic approaches. Okay, so you use these processors which ensure this deterministic implementation. So you think that determinism is fundamental in advancing this kind of the capabilities of real-time control, or that maybe asynchronism, which is easier to do in electronics.
Okay, nice question. The thing is, when you are in design stage, you have to understand which is the limit of the application, and also you have to set the closed loop sample time. So yeah, like these two bounds. Once you know at least how much it takes the code to be executed, You can also switch on a different board with an operating system and in which you have the scheduler, so you are not able to calculate in a deterministic way the execution time, but you need at least how much time do you need to execute the code in the right way. So just during the design stage. And of course, for hard real-time application, you cannot miss deadlines. So you need to use this board because, for example, in nuclear system, you cannot accept failures because of the board.
Okay, so you are really interested in having also formal guarantees, which are only enabled by these deterministic sampling times, right?
Yeah.
Okay, thank you.
You're welcome.
Let's see. Apparently, there are no further questions. So I think we are 4 minutes ahead of time, so I think we should wait anyhow, but we thank Giacomo again, and maybe we can set up an extra presentation. Thanks.
Okay, thank you.
Thank you.
I'll switch off the camera.
So maybe the next speaker can share the presentation, and then we wait a bit to start.
Yes, I'm sharing.
Davide.
Yes, just a second.
Yeah, sure. Take your time because we have time.
Okay.
Okay, we wait a bit. Still 3 minutes because maybe other people are joining.
Yes.
Yeah, so it's usually the case that you have to stop people, but
in this case, the opposite happened.
Let's see in your case. Yeah, if you see me showing up, it means that you have to stop almost. Okay, let's do like that. Two minutes to go. We were missing one of our presenter, but I'm not sure. So I can, in the meantime, check it. So it's the paper co-authored by Ankit, Gupta, and Paolo Falcone. So nobody, I guess, I cannot see the name. So here, so I guess they are not here. Oh, Ankit, sorry. So you're the presenter. Very good. Okay, very good. Perfect. Thanks a lot. So the presentation are going to take place, and I guess I can start introducing you, Davide. So next presentation is entitled A New Algorithm for Discrete Time Derivative Computation. It will be presented by Davide Tebaldi, but this is actually a joint work with the co-authors Riccardo Morselli and Roberto Zanasi.
Yes, so thank you for your introduction. So can I begin? Yes. Okay. So my name is Davide Tebaldi. I am a PhD student at the University of Modena and Reggio Emilia. And the work I'm presenting has been done in collaboration with Dr. Riccardo Morselli from Dana of Highway Engineering and Professor Roberto Zanasi, who is one of my advisors at the University of Modena and Reggio Emilia. So let me start with an observation that is the computation of the discrete time derivative of a sampled signal is actually of interest in many engineering application areas. And in particular, the context that we focused upon when we first started working on this subject was actually that of physical systems parameters estimation. And if you're interested into any further details about this work, I will remind you to the reference, which is reported here, that was presented a couple of months ago at the last IFAC World Congress. And what we did was to take some physical systems of interest in many energetic domains that were modeled using the power-oriented graphs technique. And we asked ourselves how we could estimate the physical parameters in the system physical modeling. And to do that, we had to compute the discrete time derivative of a sampled signal. And in this particular presentation here, I will be focusing on this last subject. So I will present the discrete time derivative algorithm that we proposed and that we implemented. And we will see some simulation results regarding the usage of this algorithm. So we can start by considering a sequence, x sub I, y sub I, which describes the considered sample signal. And what we can do is to interpolate the considered signal samples using, for example, a parabolic function y of x. So what we need to do next is to set up a constraint minimization problem that needs to be iteratively solved. So all the way down to the last signal sample. So for simplicity, we can focus on the first 3 signal samples, which are schematically shown here in this representation. And our objective will be that of minimizing the sum of the square distances between the actual and filtered versions of the second and third signal samples, which are y sub 1 and y sub 2. And we need to do that while having 2 constraints. So we need the parabolic interpolation, the interpolating function to be equal to the filtered version of the first signal sample, which is y sub f0 at the when evaluating at the first time sample, and its first derivative to give us the time derivative of the signal at the first time sample. So from the 2 constraints, we can actually simply find the initial expression for our parameters b and c within the parabola. And from them, we can expand the 2 distances that we are considering between the actual and filtered version of the second and third signal samples, so d sub 1 and d sub 2, and simply write them as a function of the remaining parameter a. So at this point, we can build the objective function to be minimized, that is given, as we said, by the sum of the square distances between actual and filtered versions of the signal samples. And by solving the first time derivative of this with respect to a equal to 0, we can find the missing parameter a, and eventually the final expression for the other 2 parabolic parameters b and c. So what we still have to do is therefore to find the final expression of the filtered version of our second signal sample y sub f1 and its first derivative, which is reported on the right, d sub y1. So from these expressions, there are a couple of observations to be made. First of all, what we are doing is to compute the time derivative of the preliminary filtered versions of the actual signal samples. And this is what makes the algorithm potentially robust against disturbances which may affect the actual signal samples, which typically happens in experimental setup that are available. And the algorithm, as we described it so far, actually works even in the case of non-equally spaced samples, by which I mean non-equally spaced in time, for example. So if we consider the typical case that happens of equally spaced samples, so the distance xi plus x sub I plus 1 minus xi being equal all the way down to the last signal sample, the solutions simplify as reported here in the bottom part of the slide. So to make this algorithm implementable, we actually created a MATLAB function which implements it. So if you're interested in trying or using this algorithm, you can freely download the MATLAB function from the link that is reported in the bottom right corner of the slide. So at this point, we can move to some simulation results. So we can take a continuous time signal, which is known x of t, in this case, given by the sum of some sinusoidal functions. And for such a signal, we can easily compute the exact time derivative, x dot of t. And what we need to do next is to sample our signal. So let's assume that it's sampled with a sampling time capital T over a time interval t. And in order to evaluate the results given by the algorithm, we are going to compute the discrete time derivative of the resulting sampled signal using two tools, the simulating discrete derivative block and the algorithm we propose, which does require some initial conditions. So in the simulations I'm going to present, we chose the filtered version of the first signal sample to be equal to the actual value of the signal sample. And its initial derivative simply set to the different quotient between the first and the second signal samples. This is, of course, a choice which can be freely made by the user. So here are some results. In particular, the top left subplot shows the actual signal derivative, so the one which is known analytically in a red dashed characteristic, and the discrete time derivative of the sampled signal, which is computed using the simulating discrete derivative block in green, and the blue dash characteristic shows the derivative that's computed by our algorithm. So they may seem superimposed at the first view, but by looking at the magnified version, which is shown in the top right subplot, it's possible to see that the computation which is made by Simulink does introduce some error. So the superposition is not that good in that case. So this is just a qualitative observation that we can make. And of course, we can also make some quantitative observations. So the figure of merit that we chose to use is first of all, we computed the relative errors that we have between the actual signal derivative and the one that's computed by Simulink. We normalize it with respect to the maximum value of the actual signal derivative, since it's the same, just for the sake of clearness. And we evaluated its average value, which is reported in orange dashed characteristic. And of course, we also have the same pieces of information which are reported in light blue characteristics as far as the comparison between the exact derivative and the one that is given by our algorithm are concerned. So just by looking at the order of magnitudes, it's clearly possible to see that the average error which is introduced by our algorithm is 2 orders of magnitudes, in this case, lower than that which is introduced by Simulink. So this is what we have in the case of a clean signal. We can assume we're going to add some disturbance to the original signal, d of t. In this case, it's a random disturbance, so uniformly distributed, with of course an amplitude which is sufficiently lower than that of the actual signal. And so the top left subplot in this case shows the original signal, the disturbed signal, which is reported in green, and the disturbed signal, which is filtered using the parabolic interpolation, and that is shown in red. So the top right subplot shows once again the time derivatives in a limited time fashion, just to show the better superposition, qualitatively speaking, that we have between the magenta characteristic, that is the computation which is performed by the simulating discrete derivative block, and the actual signal derivative that is in blue dashed characteristic. So once again, we can also give some, let's say, give some quantitative observation. So the orange characteristic is again the relative error between the actual signal derivative, so the one which is analytically available from the clean signal, and the discrete time derivative computed by Simulink, normalized with respect to the maximum value of the actual signal derivative, and its mean value, which is reported in orange dashed line. And same holds as far as the error which is given by our algorithm is concerned in light blue characteristic. So in this case, we actually have the same order of magnitude, more or less, but still the average error which is introduced by our algorithm is a half of the error which is introduced by Simulink. This is what we get with this particular type of disturbance affecting the signal. So to sum up, what we can say is that what I have presented is the algorithm that we employed for computing the discrete time derivative of a sampled signal, and we developed that with reference to the more general problem of estimating the physical system, the parameters of a physical system model. And the algorithm works effectively when compared with the simulating discrete derivative block, even in presence of a particular type of disturbed signal, which is the one that we have seen. And of course, this work is not over, so we are actually planning to extend this. And in particular, we still have to address the comparison of the results given by this algorithm with other solutions available in the literature, together with the comparison with the results given by Simulink that we have already made and seen. And we would like to test this algorithm with other types of noisy signals. But most importantly, the, let's say, main thing to do is to extend the algorithm to the computation of a higher order derivative of this sampled signal. And in this case, we expect that there are going to be some robustness issues which may arise as, let's say, the signal may be affected by disturbances. And last but not least, the evaluation of the impact, which is associated with the choice of the initial conditions. So we made a particular choice in the simulation results we have seen, but that's not the only one, and it may affect the algorithm performances as well, actually. So this is all. I thank you for your attention.
Thanks, Davide, for a nice presentation. So let's see if there are questions. They should appear on the chat, but I actually cannot see them. I actually have a few. So, okay, the goal is actually to recover the derivative of the underlying sample signal, correct?
Yes.
Okay, so you work under the assumption that sampling has been done according to Shannon theory.
Yes, of course.
Okay.
Yes, yes.
And then you interpolate with a parabola, a second order polynomial, correct?
Yes, so far that's what we have done.
These resemble, you know, you have zero order old, first order old, second order old for reconstructing continuous time signal from samples. So is it related to?
Well, actually, it is not related, or at least we did not start from that. Okay. So at the beginning, we simply, we actually chose a polynomial function of arbitrary order. Then we said, well, as long as our objective is to compute the first order derivative, a second order polynomial function is enough. And then we're planning to extend it to higher order polynomial interpolating function as we will move to the computation of higher order derivatives.
Because you actually keep shifting the sampling, the samples yes. That you interpolate.
Yes. Yes, exactly. That is why the computation, I mean, the choice of the initial conditions at the first step is, we have seen it is quite critical because, yes, we have to make a choice at the beginning. Then as the algorithm goes on, let's say, the impact of this choice reduces, but the initial choice is quite effective, and this is an evaluation we would like to make.
Okay, so the initialization was related to that. And you
Yes.
made the comparison with respect to Simulink, but what is doing Simulink? Probably just the difference.
Essentially, yes, the Simulink discrete derivative block computes a difference, and this is what does any, let's say, algorithm that you will find is Simulink as long as the sampling time is constant. The step size, sorry, is constant.
And since I don't see, I take advantage of the situation. So what kind of applications were you thinking about? Because you are mentioning
Yes.
parameter identification. Oh, yeah.
Yes, actually, I didn't spend much time on it. I apologize. This is related to this work. So essentially, we work with power-oriented graphs. That's a graphical modeling technique to model physical systems, and which allows to keep a one-to-one correspondence between the actual meaning of the physical parameters that appear in the model and, let's say, the actual physical system. So once the model is built, we need to estimate, let's say, the physical system parameters. And let's say to do that, we had to compute the discrete time derivative of a sample signal available from experimental data quite effectively. We noticed that as we used the Simulink, which, as you saw, there was not such a good superposition with the actual signal derivative, the estimation got worse. So this is the reason why we started working on this algorithm. It's, let's say, an alternative path to solve a larger problem.
Okay, thanks. There is a question by Alessandro Pisano. Please, Alessandro.
Do you hear me?
Yeah.
Yeah.
Yes.
My question is, if you want to estimate more than one derivative, for instance, second derivative, third derivative, can you figure out just of making a cascade implementation of your scheme, or you may think about some, let's say, more elaborated generalization that directly provide more than one derivative?
Yeah, this is exactly what we have done so far. What we have done so far is once the first derivative was computed, we employed the same algorithm over and over again, let's say, all the way up to the order of the derivation that we needed to compute. But we would like to be able to extend the algorithm from the beginning by using a higher order interpolating function.
Yes, as it is done in spline-based derivative estimation, more or less.
Yes. And next, make some comparisons and see, let's say, evaluate the results actually. Because what we have done so far is exactly what you said. So anytime we had to compute a higher order derivative, we just iterated, implemented the algorithm more than once.
Did you never tested this method in some closed loop scenario? In some experimental scenario?
No, not yet, actually. So this is something that would be interesting to be done actually as well.
Okay, thank you.
You're
Okay,
welcome.
thanks. Thanks, both of you. I'm checking if there are other questions, but I cannot see them. So I guess we can thank Davide. Thanks for the nice presentation.
Thank you.
Yeah, and then in the meantime, next speaker can set up the presentation. Thanks. We have 2 minutes. Riccardo, yes.
Start the video.
Okay. Can you see it yet?
Okay. Now can you see me?
No, the slide, no.
No, the slide, no. But
Yeah, I can see you. Yeah.
Okay,
you are on vacation.
It fits the context of this room, actually. Okay, now I loaded the slides.
Okay.
Share screen. Now?
Perfect. Okay, and we are in perfect timing. I will briefly introduce you.
Okay.
So This presentation is by Riccardo Desimini and is a joint work with myself, Maria Prandini. And the title is a Reachability Framework for Piecewise Affine Systems Verification and Control. Please, Riccardo, the stage is
for an
yours.
introduction. So in this presentation, we start with a brief introduction describing the context and the goals of our research. Next, we consider the problems of verification and robust control of piecewise affine systems and describe the applied methodologies to these problems. And then we conclude the presentation with some remarks. So the aim is to build a model-based automated tool for control and verification of hybrid systems, which are a family of dynamical systems whose evolution is governed by intertwined, continuous, and discrete dynamics. So given a model of the system and a set of specifications which may represent some prescriptions on the system trajectory or a cost function that has to be optimized subject to some constraints, the tool returns as output an answer to the addressed problem, which in case of verification is safety counterexamples or certificates, while in a control problem, it is a controller which is compliant with the specs. The tool is equipped with a toolkit of computational approaches based on reachability analysis. So starting from a set of initial conditions, the aim is to determine if the system, which is affected by input variables, which may be either control inputs or disturbances, is able to reach some prescribed region, which may be either a set of undesired behaviors that the system must avoid, or some desired behaviors that the system should maintain in order to operate in a safe or efficient way. If no control input is available, we are addressing a verification problem. Otherwise, it is a robust control problem. So the tool uses a unified modeling framework, which is the one of the discrete-time piecewise affine systems, which is a class of models whose evolution depends on the value assumed by the state inside the polyhedral partition of the state space in regions called modes. To each mode is associated an affine dynamics, which becomes activated whenever the state enters the corresponding region. Why we use this framework? For several reasons. First, despite the simple mathematical description made of linear equalities and inequalities, these kind of models have significant modeling capabilities. In particular, they are equivalent to a class of linear hybrid model, which is called Mixed Logical Dynamical, which is a class of systems describing systems with physical and logical components by means of dynamics that have mixed, continuous, and discrete dynamics. And also, these kind of models can approximate with arbitrary accuracy smooth nonlinear dynamics. Now we consider verification of piecewise affine systems subject to an additive bounded disturbance. In particular, the tool addresses bounded visibility verification and safety verification. Bounded visibility, the goal is to determine if there exists a disturbance profile that drives the system output inside an unsafe set. And this within a finite time horizon that is pre-specified. While in safety verification, one checks for the trajectories of the output if they reach a safe set in an infinite time horizon setup without limiting the space search, time search. In both cases, we consider input sequences that maximize the input perturbation, the entity of the input perturbation to be applied, so as to maintain the output inside the unsafe set. The tool addresses this problem by means of efficient reachability computations. So starting from an initial state, the idea is to compute incrementally in time the set of states that are reachable by the system dynamics for all possible inputs. This is done incrementally in time, and at each time instant, it is checked if the computed state, the computed set intersect some of the unsafe regions, and which may lead to undesired behaviors of the output. Efficiency is achieved by representing sets by means of two templates, two kinds of templates, zonotopes and constrained zonotopes. Zonotopes are centrally symmetric convex polytopes whose points are linear combinations of the center and a finite number of generators, while constrained zonotopes is a class of convex sets characterized as zonotopes subject to linear equality constraints in the generator space, and they are equivalent to convex polytopes. Now, as long as the computer sets maintain themselves inside a single mode, the dynamics of the system becomes time varying and affine, so that propagation with those templates is easy. But when a split set appears during computation, splitting among different modes, then each part of the set is associated with a different dynamics that it has to be propagated independently. Zonotopes are not closed under intersections, which implies that each part has to be outer approximated with a zonotope, thus introducing some conservativeness. This is not necessary, however, with constrained zonotopes because they are closed under intersection. We now consider the case where the computed sets intersect at some instant one of the unsafe regions. Then we want to actually determine a distribution profile moving the output to unsafety, and to do so, we first retrieve the switching sequence that originated the intersection with the specs, and this implies that the system becomes invariant and affine, so that we can compute the maximal input perturbation to be applied so as to drive the output at the specs, unsafe spec set at the predicted time instant for all possible perturbation. This problem can be reformulated as a linear program, which can be infeasible only if conservativeness was introduced during reachability computations. The main challenge to deal with this kind of approach is the combinatorial explosion of the number of generated branches of sets, which has a worst case exponential rate of growth with respect to the earliest specs violation time. So to mitigate this combinatorial explosion, we devised 4 strategies. One is set containment verification, which consists in halting the propagation of the newly computed sets which are included inside the previously computed ones. The second one is invariant sets computation, which involves computing in robust invariant sets that are included inside some polyhedral region that are computed in turn so as to avoid specifications. In particular, we then check if the computed rich set is included inside the invariant so that we can halt its propagation due to the invariance property, since it does not intersect the specs by construction. Note that these 2 methods both allow to address safety verification also on an infinite time horizon, and not only for bounded feasibility. The third method is clustering of sets, which consists in grouping sets inside a single mode into one, and to propagate the group of set as a single, thus reducing the number of branches. And the fourth one is mode reduction, which consists in constructing groups of mergeable modes by means of an heuristic approach, which collects pairs of modes and which have same dynamics and convex union. Now we consider a numerical example for bouncing ball, as shown in the slide. The ball is thrown with an initial force F0 and then is left evolving of free motion. We aim at computing the minimal time instant at which the ball hits the unsafe region PSP after a prescribed number of bounces, MB min. The system state is made by the number of bounces, the position and velocity component of the ball, and the scalar used to transmit the acceleration only at the first time instant. The input is acceleration component of the ball. The system dynamics is split into 4 regions, each representing the behaviors of the ball. One is motion and bounce when the ball is subject to a force, and motion and bounce when no force is applied. We want to compare our approach with an alternative method based on mixed integer linear programming. The comparison is made in terms of the computing time with respect to the various minimal number of prescribed bounces of the ball. In this approach, we reformulate the system as a mixed logical dynamical, which is made of linear equalities and inequalities with continuous and binary variables, so that the verification problem reduces to mixed integer linear programming. However, if the minimal solution time is not known, one has to solve a number of increasingly high mixed integer linear programs in the time horizon 0t, which increases with t. And instead, if the minimal solution time is available to the solver, it is sufficient to solve a single MILP on 0t, t-min, which is known. As one can see in the table, the reachability computations perform better when the time horizon length is large. This happens also when the minimal time instant is not available to an MILP solver. And this is due to the combinatorial complexity of mixed integer programming, which becomes worse and worse as the number of binary variables increases. We now address robust control of piecewise affine systems that are subject to uncertainty. The uncertainty enters the systems in terms of an additive disturbance with bundle support and not accurately known initial state, which ranges inside a region xi. The aim is to design a state feedback controller that drives the system, the state, to a target set, xf, while also maintaining the trajectory inside a collection of assigned safe sets despite uncertainty. This problem is addressed by the tool by the following procedure, where we compute an admissible switching sequence for the nominal system, that is, systems without uncertainty. This is done with reachability analysis as shown in the previous slides of verification. And then by means of linear programming, we assign a robustness level to the computed sequence, which account for the amount of uncertainty that can affect the system in such a way that the safety and actuation constraints are satisfied, and also the same mode sequence is maintained by means of an open loop controller. Second stage, we parameterize the state feedback controller by means of a linear combination of the control actions applied to the syntax and the generators of the zonal topic closed loop reach set. This has the advantage to provide better scaling properties with respect to the parameterization based on the vertices of the reach set. So we designed the state feedback controller in such a way that we track the switching sequences with the highest robustness level, while also satisfying the safety and the actuation constraints. Indeed, as long as the reach sets are included inside a single mode, the dynamics becomes time varying and affine, and so the state feedback controller design reduces to a linear program. If splitting occurs, one has to propagate, to branch each part of the zone top according to a newly generated switching sequence. We now consider an example of a second order system, as shown in the slide. The system has 6 modes and is subject to a safety specification represented in terms of a polyhedral region in blue that has to contain the system trajectories, and also some actuation constraints in terms of parameterized intervals. The uncertainty enters the system by means of initial state and disturbance, which range inside some parameterized intervals as shown in the slide. We want to compare our method with an alternative tube-based approach from the literature. The comparison is made in terms of the capability of the controller to track the assigned switching sequence and also satisfying the safety and actuation constraints. The tube-based approach parameterizes the control input by means of a convex combination of the control action applied at the vertices of the corresponding tube section, which is parameterized by means of a point Z and a scaling factor, eta. However, its shape is fixed a priori by means of a template polyhedron TSH. We now consider this to-pass amplitude of 0.4. And in this case, both approaches are feasible and are able to satisfy constraints and track the assigned switching sequence. Whereas if we increase the amplitude to 0.5, the tube-based approach becomes infeasible. This is because it imposes a structure to the shape of the tube. It is conservative, so that it may lead prematurely to infeasibility when constraints become tighter. This is not the case in our approach, since in this problem instance, computation are exact. So we developed a reachability framework for discrete time systems, piecewise affine systems. In the verification part, our reachability method exploits the structure of the pure dynamics and is able to provide better scaling properties with respect to alternative mixed integer linear programming approaches, while the robust control part, our controller, is based on reachability analysis, this with tighter constraints with respect to alternative methods tube-based, where the geometry of the tube section are fixed. Thank you for your attention.
Thank you, Riccardo. So in this case, I cannot make questions. So is there any question from the chat? I cannot see anyone. I have one, Alessandro Pisano, please.
It's more a curiosity than truly a question, because I'm not a very expert of this kind of approach. My question is it possible to obtain this kind of results also in the continuous time setting? I mean, are these kind of results already been achieved and this is a generalization, or it is a totally different scenario?
Okay, allora, well, in this approach, yes, the answer is yes. There are verification methods in continuous time. There are tools dealing with it in continuous time, but in different frameworks. So, for example, you can consider the hybrid automata case, while we here consider discrete time piecewise affine systems. Also, there are other approaches in continuous time of control, but typically, if you consider model predictive control, it is made on discrete time. So this optimal control approach is actually designed to be extended to an MPC setup.
For verification in continuous time, which kind of mathematical tools are needed? I don't know, LMIs, how
they use analysis, they compute exponential matrix of the dynamics and use some approximation procedure. So actually they reduce to discrete time computation in the sense that they compute, they discretize the time, but they compute outer approximations that are valid also for the intermediate parts. This is the difference.
So in some sense, they approach the discrete time scenario as well, even starting from the continuous time.
For computational reasons, yes.
Thank you.
I cannot see other questions. Let's see, let's wait. Otherwise, we thank Riccardo. Okay, yeah, thank Riccardo. I cannot see, I mean, no question is showing up. Thanks, and we can move to the other speaker. Next speaker, thanks again. So the next speaker is Ankit Gupta. So I would suggest to share your presentation and show up. We have 2 minutes, but I guess by the time we set up. Okay. Hello?
Is my slides visible now?
Yeah.
Right. So I just
Perfect.
wait for maybe a minute.
Yeah.
All right.
Just wait 1 minute and then I will introduce you. Thanks.
All right. Perfect.
Perfect. Almost ready. Let me check. Okay. I guess I can start introducing you. So first of all, the title of the presentation, Full Complexity Characterization of Control-Invariant Domains for Systems with Uncertain Parameter Dependence. And this is a joint work of Ankit Gupta and Paolo Falcone. from Chalmers University of Technology.
All right.
So I guess you can start. Thanks.
Good afternoon, everyone. Thanks for listening to the presentation. So today I will be presenting one of my recent work, which was also presented in CDC 2018. So let's directly go into the details what we have done. So basically, in this paper, we proposed an algorithm to compute a robust control invariant set of predefined complexity, so user can select what complexity or control invariant set they want. Before going into the computational details of the problem formulation, let's see the main objectives and the motivation behind the research. For that, we first go through the definition of RCI set. We say a set C is a robust control invariant if given any initial point within the sets, there always exists an admissible input which brings me back to that set for all the possible disturbances and uncertainties. And basically, these sets are widely used within many control applications for example, for stability analysis, controller synthesis, and vice versa, and etc. But one of the main application is in MPC control strategy design, where these sets are used as terminal constraints to guarantee persistent feasibility of MPC scheme. And this set basically affects many features of MPC controller. For example, complexity of the MPC controller is directly proportional to the complexity of these terminal constraints, as well as the volume of the feasibility set of the MPC controller is also proportional to the volume of these sets. And as we said, as I said before, that we want to compute RCI set with adjustable complexity and large volume because it directly affects the required feature in the MPC controller. And the main motivation here is that we want to trade off the complexity of overall MPC algorithm with the feasibility set. So this will be the main outline of my talk today. So we directly move on to the problem formulation. So in our formulation, what we consider is a system which is rational parameter dependent system. Basically where the rational parameters enter system dynamic rationally. For example, if we consider this two-dimensional system, we can see that the parameters here, they enter rationally within the system matrix A. And this kind of system can be exactly represented by the considered system in the formulation. And this is basically quite a good advantage because most of the current algorithm, what we see, can only handle affine or polytopic system representation, whereas the proposed approach can handle more general type of system descriptions. Further, we consider a linear controller which induces invariance within the considered set. And in our formulation, we assume that this control law K is unknown and it will be computed by the algorithm. We assume that the system is under some polytopic state and input constraints, as well as the additive disturbance, which is acting on the system dynamics, also belongs to some bounded polytopic set, as well as the uncertainty. Since we want invariance set to be of predefined complexity, so we have to impose some restrictions on what kind of set we want. So we consider a zero-trauma symmetric set, where P matrix is a user-defined matrix, and it is it basically defines the representational complexity of the invariant set, whereas W is a matrix which will be computed by the proposed algorithm, such that the set will be of desirably large volume, as well as it has the property of invariance within it. To sum up the whole thing, what we want to do in this paper is to compute an invariant set C, which has desirably large volume, has the property of invariance, satisfies the state constraints, and the control law K, which will be computed, should also satisfy the input constraints. So basically, we want four things in this. We want to formulate four things in this paper. For the tractable formulation, what we do is we first introduce a state transformation, and we introduce a new state space theta, which is related to the original state space by a matrix W. And as we said, W is the unknown, and it is computed by the algorithm. So we can say that this state space transformation is unknown. But the advantage of using this state space transformation is that the candidate invariant set theta in the transform space is basically known, because P is a user-defined matrix. So for the toy example, if we consider a P matrix as shown, then we basically know the candidate invariant set in this theta state space. So basically, we also know the vertices theta of this set. Using this information, actually, we can redefine the state and input constraints as follow. So the state constraints, since we want that the invariant set should satisfy the state constraints, basically in the theta state space, we can rewrite this equation as follows. And since we know that theta is a polytopic set and we want to satisfy this for all theta, so the necessary and sufficient condition is to satisfy these constraints on the vertices of the set theta. And similarly, by introducing a new variable n, as shown, we can rewrite the input constraints in linear form as shown. And throughout the presentation, we will use the colored variable just to indicate that these are unknowns and will be computed by the algorithm. So now we have tractable formulation for the state and input constraints, which are linear. Next, we move on to the invariance condition. For invariance condition, what we do is we introduce, you go back to the definition, which means that if theta belongs to my candidate set, then theta plus should also belong to my candidate set. And this condition can be written as a positivity condition on the as shown. And then using standard LMI tricks, that is using some identity, S procedure, and some other manipulations, we can rewrite this invariance condition as LMIs, which is represented by calligraphic LI in this slide. So basically this represents my linear LMI condition for invariance. So now we have most of the required constraints, all of the required constraints that are invariance, state, and input constraints. The only thing which remains right now is the cost function, which we want to maximize. Since the invariant set, candidate invariant set is user-defined, has a user-defined complexity, to maximize the volume of such a set, what we do is we introduce an ellipsoid. And the reason for that is because we know how to maximize or minimize the volume of ellipse, because it is proportional to the shape matrix of the ellipse, the determinant of that. So then we inscribe this ellipsoid within the candidate invariant set, and then we try to maximize the volume of this ellipse. And because of this, we have to introduce another condition, which is calligraphic SI, basically which represents that the ellipsoid is inscribed within the candidate invariant set. So to sum up the whole thing together, the final algorithm looks like this. So here we have polytopic state constraints, input constraints, the LMI condition for invariance, then the cost function, which represents the volume of ellipsoids, and the condition which basically says that the ellipsoid is inscribed within the candidate invariant set. Next, what we do is do the numerical implementation of this algorithm on the proposed on the 2D example, which we considered in the beginning of this presentation. So we start with the minimum complexity polytope, candidate polytope, where the NP is equal to 2. This is minimum because to have a bounded polytope. And we can see that the volume is 58.6, which was computed using MPT toolbox. By slightly increasing the complexity just by 1, we can see that we can see a drastic improvement in the volume. And by further increasing the complexity, we can see we can even find a better invariant set, which has a larger volume. So clearly we can see that we can trade off the complexity here with the volume of the invariant set. Next, we do another numerical example on the proposed algorithm, in which what we do is we consider any disturbance or uncertainty which is acting on the system and increase the bound on that disturbance and try to compute invariant sets of different complexity and see when the algorithm becomes infeasible. So by doing this experiment, what we found, for example, here we consider delta 1. So when we do this experiment with the parameter delta 1, we see that with complexity 2 and 3, the algorithm becomes infeasible after 0.35, when the bounds on delta 1 is 0.35. And similarly, what we see is that, we see the same effect when we consider other disturbances and uncertainties, that with the higher complexity, we are able to compute invariant set even for the larger values of disturbance and uncertainties bound. So this also shows that complexity can also be used as a additional tuning parameter here to be able to compute invariant sets. So to end my presentation, I will like to make some concluding remarks. First is the preliminary achievement. What we have achieved using this results is that first, we have proposed a algorithm which computes invariant set of desirably large volume and predefined complexity. Then this approach is applicable to rational parameter dependent system. And further, we can also compute an invariant set of desirably small volumes just by inscribing invariant set within the ellipse and then minimizing the volume of this ellipse. Of course, since I had to hide many mathematical details of this algorithm, how we derive the LMI constraints, because originally these constraints were linear. So because of that, there are some drawbacks of the proposed method. First is like selecting the matrix P, which is a user-defined matrix, and user has to propose some, think of some method, how to select this. And of course, for that, you need some idea how the invariant set looks like. One simplest method how to select the matrix P could be to select initial polytope which is close around the origin, and then of desired complexity. And the reason for doing this is because it will definitely satisfy state and input constraints, and by selecting the matrix W appropriately, the invariance can be induced within this set. And of course, as I said, that the original conditions were non-linear. Because of this, if we say that the algorithm is infeasible, we cannot say that the RCI set as well as the controller doesn't exist. So that kind of statement cannot be made. As well as since we can relate it to the same that the solutions which we found are globally optimal. In case someone is interested into going into the details of what we have done in this paper, again, find in the paper that is already available online in IEEE control system records. Thank you.
Thanks a lot, Ankit.
Sorry?
Thanks a lot for your presentation. So it's over, yeah. And I would like to ask if there are any questions from the audience. Otherwise, I can start. Okay, so regarding the ellipsoidal set that you use to enlarge the volume of the invariant, so do you need to fix the shape
of the initial polytope?
No, the ellipsoid.
No. It will be computed by the algorithm directly itself.
Okay, also the orientation.
Yeah, exactly. And first, recently in a new paper, which is right now under the review, we have even shown that actually we do not need the ellipsoid. We have proved that the volume of the invariant set, such a candidate invariant set, is actually proportional to the determinant of the matrix W. So we do not have to even maximize the, we do not have to introduce ellipse here.
And this matrix value, W, you always write the inverse because it's for sure invertible and numerically, I don't know, I saw in a few times that you are using the inverse of this matrix, which you don't know. Correct.
The thing is, we wrote it as inverse in the start is because in the LMI condition, then it appears as a matrix W. It's just for, we don't want to see any inverse term in the conditions. That's the reason. But the algorithm guarantees that matrix W will be invertible. Yeah.
Okay.
It is guaranteed by the LMI condition of invariance, actually.
Okay, and this K enters linearly. Okay.
Yeah.
Okay, it's very interesting. Yeah. So is there any other question? Apparently no. So the class of systems, you are saying that the parameters can enter in what way? So you made an example of linear parameter varying systems,
Yeah.
but the class is more general
Yeah.
than this. So what are the, I mean, what's the assumption regarding the dependence on the parameter?
The parameters should be bounded, as well as it should be well posed. By well posed, we mean that this matrix should be invertible.
Okay.
Early. So if we are able, and this is quite, it's standard thing in the robust control. So yeah, and we can actually model very vast class of system using this representations. For example, if we have a nonlinear systems, we can represent them using this system descriptions.
Okay. Now it's interesting that you can actually tune this K because you decide the K, correct?
Yeah, exactly. So the K is optimized.
Which is quite unusual.
For the RCI set, yes.
Yeah. Usually you fix and then you find the invariant because through the dynamics it ends up being not a linear dependence, but you found the trick to get it treatable.
Yeah, exactly.
Which
so
is,
the main trick was to use the state space transformation, which helps us a lot to formulate it in the tractable way.
I see. Yeah, it's very nice. Maybe Alessandro has a question, I'm not sure, because in the chat there is a list of I have questions. Maybe not.
All right.
I have another one because usually the problem is also the order of the system to make the problem treatable. Do you have any issue with that, or it scales?
Yeah, we have this problem with the system dimension. So what we have done is we tried with many systems, and we found that like after 5-dimensional or 6-dimensional systems, then the computation becomes too heavy for the actually present SDP solvers.
Oh,
and yeah, because I feel like this is something which is lacking when we compare it with the QP and LP solvers, that SDP solvers currently available are not, that much, like, what do you say, good or this thing. Because many times when you solve the same problem with the different solvers, you many times get different results. Even though the problem is convex and theoretically this shouldn't happen, but yeah.
We know. Yeah, you should ask also Riccardo. No, because I was wondering when you say that you can control the complexity of your set representation, but actually as the dimension grows, it becomes naturally more complex. Very simple. So yeah, scalability, it's always an issue.
Yeah, exactly.
Okay, so I see no questions. We thank you again for the nice presentation and interesting work.
Thank you.
And then I think we can move to the next speaker. She can set up the presentation. Thanks.
Thank you.
Bye-bye. Okay.
Are you able to see my screen?
Yeah, perfect.
Okay.
We just wait 1-2 minutes.
Okay.
You are too good. Okay, I think I can introduce you, Carmela. So the last presentation of this session will be done by Carmela Bernardo. This is a joint work with Francesco Vasca. Francesco, yeah, I was sure. And the title of the presentation is Hegselmann Krause model in mixed logical dynamical formulation. And we are almost ready to start because it's, yeah, 1 minute. I think you can start, Carmela. Thanks.
Okay, thank you. Good afternoon to everyone. I am Carmela Bernardo, a PhD student from University of Sannio, and I'm going to present the work entitled The Hegselmann-Krause Model in Mixed Logical Dynamical Formulation, carried out with my advisor, Professor Francesco Vasca. The main goal of the work is a new formulation, in particular a mixed logical dynamical formulation of the Hegselmann-Krause opinion dynamics model. So firstly, I will introduce the Hegselmann-Krause model. After that, how we obtained the mixed logical dynamical formulation. Then I will show some numerical steady-state analysis, and finally, I will provide conclusions and future directions for exploration of the proposed model. Consider a network of n agents whose opinion at time step k is described by the state variable xi, and we assume that this variable has a value within the interval 0, 1. The time evolution of the opinions depends on the interaction among the agents in the network, and in particular, according to the Hegselmann-Krause model, the interaction between two agents occurs only if they have a similar opinion, and the opinion of the agent I at time step k plus 1 represented by xi plus is given by the mean of the opinions of the agents which interact with the agent I, called the neighbors. Indeed, from this equation, the summation is the sum of the opinions of the neighbors, and nu I represents the number of the neighbors. X is a column vector of all opinions. The term 1 divided by nu I is called susceptibility of the agent I. Phi j is the influence function which determines if the agent I is influenced by the agent j. So the influence function is equal to 1 when the agent j is a neighbor of the agent I. The influence function phi j is based on a threshold policy depending on the difference xj minus xi. In particular, the influence function phi j is equal to 1 when the difference between the opinion of the agent j and that of the agent I is within the interval minus dig and dic. Otherwise, phi j is equal to 0. The interval minus dig dic is called the confidence interval of the agent I, and the lower bound dig is called the generosity threshold, while the upper bound dic is called the competition threshold. Since the agents in the network can assume different confidence intervals, it may happen that the agent I is influenced by the agent J, but the agent J is not influenced by the agent I. For example, in this figure, the two influence functions phi ij and phi ji are shown. When the difference between the opinion of the agent J and that of the agent I is within this interval or this interval, the agent I is influenced by the agent J. Indeed, phi ij is equal to 1, but the agent J is not influenced by the agent I. Indeed, phi ji is equal to 0. In relation to the value assumed by the confidence intervals, we can provide two different classifications of the Hegselmann-Krause opinion dynamics model. Firstly, the model is said symmetric when the generosity threshold is equal to the competition thresholds for all agents, and it is asymmetric otherwise. Moreover, the model is said homogeneous when all agents have the same confidence interval, and it is heterogeneous otherwise. The confidence interval determines the behavior of the Hegselmann-Krause model. In particular, in this slide, 3 different simulations are shown. These simulations are obtained by considering 100 opinions starting from a uniform distribution of the initial opinions, and in particular, we consider the homogeneous Hegselmann-Krause model, that is when all agents have the same confidence interval. In the first simulation, the model is symmetric with the value of the thresholds equal to 0.3. Each colored line represents the time evolution of a single opinion. The x-axis is the time, and the y-axis represents the value of the opinions that is within the interval 0, 1. Here we can see that after some time, all opinions reach a common value. This situation is called consensus. In the second simulation, the model is symmetric, but with a lower value of the thresholds. Indeed, the thresholds are equal to 0.15. Here, after some time, the opinions form 3 different groups called clusters. In the last simulation, the model is asymmetric with a competition threshold greater than the generosity threshold. Here, the consensus is reached, but the consensus value is greater than the consensus value of the first simulation. So, starting from these 3 simple examples, we can say that in order to reach the consensus, we need that the confidence thresholds are sufficiently wide, and the consensus value depends on the values of the thresholds. As I have already said, the main goal of this work is to provide a new formulation, a mixed logical dynamical formulation of the Hegselmann-Krause opinion dynamics model. In order to obtain this representation, we need of some typical expressions which involve real and logical variables. In particular, we used these 3 MLD equivalences. The logical variable mu that is equal to 1 when the real function f(x) is less than or equal to 0 is equivalent to this set of inequalities. Moreover, the product between the real function f(x) and the logical variable mu equal to the real variable w is equivalent to these 4 inequalities. Finally, the AND operator between the 2 logical variables mu1 and mu2 equal to the logical variable mu3 is equivalent to these 3 inequalities. Epsilon is a small positive parameter. Lowercase m and uppercase m represent a lower bound and an upper bound of the real function f(x) respectively. In this part of the slide, the steps that we followed to obtain the mixed logical dynamical formulation of the Hegselmann-Krause model are shown. Starting from the Hegselmann-Krause model, firstly, we transformed in MLD the influence function, after that the susceptibility, and finally the model equation. So consider the influence function phi(ij). The inequality in its definition can be written through these 2 inequalities. So now we need to introduce 2 logical variables, delta ijc and delta ijg, for each pair ij. Delta ijc is equal to 1 when the first inequality holds, while delta ijg is equal to 1 when the second inequality is valid. These 2 equivalences can be written as a set of inequalities presented in the previous slide. Since the influence function is equal to 1 when both these inequalities are valid, we need to introduce a further logical variable delta ij that is given by the AND operator between the 2 logical variables delta ijc and delta ijg. Since delta ij is equal to 1 when both these logical variables are equal to 1, it follows that the influence function is equal to the logical variable delta ij. As regards the susceptibility that is given by 1 divided by the number of neighbors, we need of another logical variables mu ik for each pair ik. Mu ik is equal to 1 when the sum over j from 1 to n of delta ij is equal to k. So this variable is equal to 1 when the agent I is influenced by k neighbors. Since at each time step the number of neighbors of the agent I is unique, for each I only one variable mu ik is equal to 1. So it follows that the AND operator between the two logical variables mu ik1 and mu ik2 is equal to 0 for all k1 not equal to k2. By using this logical variable, the susceptibility of the agent I, 1 divided by nu I, can be written as the sum over k from 1 to n of 1 divided by k times mu ik. The last step to obtain the mixed logical dynamical formulation of the Hegselmann-Krause opinion dynamics model consists in transforming the model equation. So, starting from the original Hegselmann-Krause model and by substituting the new formulation of the influence function and that of the susceptibility, the Hegselmann-Krause model can be written in this way. Now, the product between the two logical variables mu ik and delta ij can be written as another logical variable gamma ijk. Gamma ijk is equal to 1 when the agent I is influenced by the agent j and other k minus 1 neighbors. By using this logical variable, the Hegselmann-Krause model can be written in this way. Finally, the product between the logical variable gamma ijk and the state variable corresponding to the opinion of the agent j xj can be written as a new scalar variables wijk. In this way, the final formulation of the Hegselmann-Krause model mixed logical dynamical formulation becomes this. The opinion of the agent I at time step k plus 1 represented by xi plus is given by the sum over j from 1 to n of the sum over k from 1 to n of 1 divided by k times yijk, together with the set of inequalities corresponding to the variable defined above. This set of inequalities can be also written in matrix form as shown in the slide. Finally, we have also provided a steady state analysis in order to understand the relationship between the confidence intervals and the consensus and the clustering. In particular, these simulations are obtained by considering 100 opinions starting from a uniform distribution of the initial opinion, and we take into account the homogeneous asymmetric Hegselmann-Krause model. In particular, each figure is characterized by a fixed value of the confidence interval. So, by varying the competition threshold on the x-axis, the generosity threshold is given by the difference between the confidence interval and the competition threshold. The color represents the number of agents belong in a range of opinions of amplitude of 0.05 when the system reaches the steady state. So the y-axis is divided into ranges of amplitude 0.05. From these simulations, we can see that the consensus is reached only when the confidence interval is of at least equal to 0.5. And when the confidence interval is equal to 0.3 and 0.4, corresponding to the second and third simulations respectively, we have the consensus only for high values of the competition thresholds or of the generosity thresholds. Moreover, the consensus value increases with the competition thresholds and decreases with the generosity thresholds. So, a more competitive behavior of the agents helps to reach a higher consensus value. When the competition threshold is equal to the generosity threshold, so when the two thresholds are equal the half of the confidence interval, the consensus value is equal to 0.5. So the preserving average condition is satisfied. By concluding, in this work we have provided a mixed logical dynamical formulation of the Hegselmann-Krause opinion dynamics model and the set of inequalities that describe the model depends linearly on the confidence thresholds of the agents. Moreover, we have provided also a steady-state analysis in order to capture how consensus and clustering depend on the confidence thresholds of the agents. And in particular, we need of confidence thresholds sufficiently wide to reach the consensus, and the consensus value increases with the competition and decreases with the generosity. As regards future work, we would like to find sufficient conditions for the convergence to the clusters and the consensus by using the stability theory for mixed logical dynamical systems. Thank you for your attention.
Thank you very much, Carmela, for your presentation. I have some questions. I will start. So I was wondering, this framework helps in what direction does this framework help you? Just in analysis or possibly in control, like affecting the dynamics, opinion dynamics?
I would like to find the stability of the model, because now the stability of the Hegselmann-Krause model is an open problem, since this model is a nonlinear model and its behavior is very, very complicated. But so we would like to find, to use some results that are already in literature to find the stability of the model.
Okay, so your goal now is analysis.
Yeah.
Okay, it's not how to affect behavior by exploiting the structure. Okay, I see that there are questions from Mauro.
Yes, thanks.
Yeah.
So one thing I didn't pick up from the presentation. So what kind of graphs are you considering? Are they structured graphs, like a complete graph, or
the graph is based on the influence function. I mean, the graph is a direct graph, and there is a
directed or undirected?
Directed. Yeah.
Okay.
And there is a connection between the agent from the agent I to agent J if phi ij is equal to 1. I mean, if the agent I is influenced by the agent J, there is a connection from the agent I to the agent J.
Okay, so you assume that the graph is arbitrary, but it is strongly connected, or something like that?
No, it's not necessary that is strongly connected, because if it is not connected, probably there is a situation like this, there is a situation of clustering.
Okay, but then also another question. So in the symmetric model, your definition of symmetry and asymmetry,
Yeah.
You're assuming that the parameters DC and DG are different from for every edge.
Yes.
Okay. Okay, so there is, but in the result, in the sufficient conditions so that you aim to achieve, you want to consider bounds on these parameters. I mean, what I mean is that the problem is incredibly complex. Okay, so because there are so many parameters, so it also depends on the initial conditions, and so you propose to use mixed logic dynamical programming, so that you have mixed logic dynamical systems, so that you have a different tool to study this problem. But then in the numerical simulations, you consider some simplifications. So what is I mean, the sufficient conditions that you aim to achieve are what kind of simplified scenario are you looking at to find a sufficient condition for convergence, or are you looking at the most difficult scenario?
In literature, there are already some results for symmetric and homogeneous model. So I would like at least to find sufficient condition for the asymmetric homogeneous model.
Okay. Okay, thank you.
Thank you.
Thanks a lot.
Thank you.
Okay, I cannot see any other question, and also time is over. So perfect, everybody. I would like to congratulate with everybody of you. That was very timely and perfect. Very nice presentation. And this actually concludes this session. Thanks a lot to everybody. Bye.
Bye.